One ordinary day at work or at home, while you're busy with your usual activities, you suddenly realize that someone is spying on you, not with surveillance cameras, but with Wi-Fi technology. Come, let me explain how. Using your home Wi-Fi, you can monitor your movements just like a thermal camera. Yes, you heard that right. With today's advanced technologies, wireless signals aren't just for internet connectivity, they also act as a sophisticated sensor. In this video, we'll show you how the information extracted from Wi-Fi signals, CSI, can help artificial intelligence determine your location and even your body posture. This technology is like a double-edged sword. On one hand, it takes your smart home experience to a whole new level, but on the other, it raises concerns about privacy. Are you ready to join us and take an in-depth look behind the scenes of this technology? We'll explore everything from how it works to its fascinating applications and security challenges. So, stay tuned as we uncover the secrets behind smart Wi-Fi. On this slide, you can see the four main sections we'll be covering today. Holography of Wi-Fi radiation. Here, I'll explain how Wi-Fi waves can be visualized or mapped to form holographic-like images, image Wi-Fi. Next, we'll explore methods for creating 2D or even 3D images using Wi-Fi signal reflections, skeleton detection in Wi-Fi. Then, I'll discuss how researchers can detect human movement or skeletal outlines through Wi-Fi signals, diagnosis methods. Finally, we'll look at various diagnostic or analytical methods that use Wi-Fi data for sensing, monitoring, or potentially spying. Each section is based on real scientific articles and studies, so let's begin by diving into the first topic, holography of Wi-Fi radiation. We see a fascinating experiment that illustrates Wi-Fi holography. Researchers placed a cross-shaped object between a standard Wi-Fi transmitter and a receiver to observe how the signal disperses and interacts with obstacles. On the left, there's a diagram showing the Wi-Fi wavefront, labeled with its intensity and phase, passing around the cross before it reaches the receiver. On the right, we can see an actual photo of the cross-shaped object, wrapped in reflective material. The idea is that by measuring tiny changes in how the signal is scattered, researchers can create an interference pattern or a hologram. Essentially, this captures both the amplitude and phase of the Wi-Fi waves, allowing us to reconstruct a detailed image of the object. Even though we're working with invisible signals, this experiment helps demonstrate that with the right equipment and algorithms, Wi-Fi can be used to gather spatial information about objects in a room. It forms the foundation for the concept of Wi-Fi holography, which we'll explore further in the next slides. Here we have a simplified illustration of how Wi-Fi holography works. On the right-hand side, you see a standard Wi-Fi transmitter sending out circular wavefronts. These circles represent the wireless signal spreading outward. Then, in the center, we have a cross-shaped object. As the Wi-Fi waves encounter the object, they scatter around it. On the left, we see a visual representation of the wavefront labeled with two important factors, amplitude and phase. In mathematical terms, it's shown as I, x, y, multiplied by e caret, I phi, x, y. That's just a fancy way of saying the waves have both a strength, called intensity, and a shifting pattern, called phase. Finally, there's a receiver antenna at the bottom right that picks up the altered signals after they've passed around, through, or been reflected by the cross. From this scattered data, researchers can reconstruct a hologram, an image that captures how the object influenced the waves. Why is this significant? By analyzing these subtle changes in amplitude and phase, we can learn a surprising amount about the shape, position, and even material properties of objects, even if they're not in direct line of sight. This lays the groundwork for Wi-Fi-based imaging techniques that could theoretically be used for surveillance, or, as we're calling it, Wi-Fi espionage. We see the signal processing steps researchers use to create a holographic image of the cross-shaped object. First, the Wi-Fi transmitter on the left sends out a signal that interacts with the cross. The receiver collects the scattered data, and we end up with an initial heat map-like image, the one in blue and red. Next, they apply a mask to the data. This mask helps filter out unwanted noise or background reflections, so that the most important signal elements, those coming from the cross, are emphasized. In the middle step, labeled B, you can see the result after certain areas of the data have been suppressed. Finally, they subtract B from the unmasked data to isolate the cross's signature even more clearly. The image marked C is the enhanced reconstruction of the cross, showing the most intense signal reflections in red and orange. Essentially, this step-by-step process reveals how the Wi-Fi waves are distorted by the object, allowing researchers to see its shape without any direct line of sight. These techniques are part of what we call Wi-Fi holography. They capture both the amplitude and the phase of the Wi-Fi signal. By carefully removing background interference and highlighting the key reflections, we can produce a surprisingly clear representation of the object in question. This slide demonstrates how Wi-Fi holography can go beyond flat, 2D images and into 3D reconstructions. On the left, you see a simplified cutaway of a building or a room. There's a Wi-Fi transmitter at the bottom, shown in blue, which sends signals up through multiple floors. On the right, you see 3 separate slices or layers of data. Each slice represents a horizontal cross-section of the space at a different height. The colors, blue for lower intensity, yellow to red for higher intensity, indicate how the Wi-Fi signals are reflecting off objects in each layer. By stacking these slices, researchers can piece together a 3D map of what's inside the building, capturing details like walls, furniture, or other objects. Essentially, the signals bounce off various surfaces, and the system's algorithms measure phase and amplitude changes. From that information, they generate a volumetric image. In practical terms, it's like doing a Wi-Fi-based CT scan of the room, but without any specialized X-ray equipment. This could be used to locate hidden structures or people behind walls, an application that's both fascinating for scientific research and potentially concerning from a privacy standpoint, which is why we often refer to it as Wi-Fi espionage. Next, we'll see how these 3D reconstructions can become even more detailed as researchers refine the antenna setups and apply more advanced signal processing methods. Here, we're looking at how standard camera images compare to images derived from Wi-Fi signals. On the left, we have a normal RGB image of a person holding a laptop. The face is blurred for privacy. In the center, we see a Wi-Fi image, which is essentially a heat map showing the strength of reflected signals from the person's body and the laptop. Then on the right, we have what's called the YSIA mask. It's a silhouette, created by analyzing where the Wi-Fi reflections are strongest. The black area represents the person's body outline, while the pink area highlights the laptop. By thresholding or filtering signal intensity, researchers can isolate the general shape of objects, which you see here as a simple black and white contour. Even though it's not as detailed as a regular photo, this silhouette still gives us valuable information: the height, general body shape, and even an idea of where someone might be holding an object. This is the basis for Wi-Fi imaging, transforming raw signal reflections into recognizable silhouettes or 2D shapes, all without using a traditional camera. Of course, the resolution isn't as high as a typical camera image, but it's surprisingly revealing. When you combine these silhouettes with more advanced algorithms, it's possible to track motion, detect objects, or even identify certain postures. That's why we're calling it Wi-Fi espionage, the idea that regular Wi-Fi signals could be used for surveillance or monitoring, just like a camera. Using 60 GHz Wi-Fi, we achieve more detailed imaging. However, the penetration of this signal through walls increases, so the information is only analyzed within the environment. We see how researchers can detect the human body's key points, like the head, chest, arms, and feet, by analyzing Wi-Fi signals. The technique, often called RF capture or RF-based pose estimation, works by sending radio waves from a Wi-Fi transmitter, which bounce off a person's body and return to a receiver. As the person moves, the system collects multiple snapshots of these reflected signals over time, shown on the left in a series of blue and red heat maps. Each red or yellow spot represents a strong reflection. By comparing the time and strength of these reflections, the algorithm locates various body parts: head, hands, feet, chest, and so on. On the right, we see an annotated map where each body part is labeled. The system pinpoints these areas by calculating the signal's attenuation coefficient, basically, how much the wave is dampened or reflected by different parts of the body. These coordinates are then matched to a real image of the person, blurred here for privacy, To confirm how accurate the detection is, this allows Wi-Fi-based systems to track a person's skeleton or pose in real time, all without using a camera. Imagine being able to see through walls or in the dark, purely from the wireless signals bouncing around. It's both an impressive technological breakthrough and a potential privacy concern, which is why it's often referred to as Wi-Fi espionage. Next, we'll see how these skeleton detection methods can be used in various applications, from security and health monitoring to advanced motion tracking. Here, we're looking at how Wi-Fi systems can determine a person's position and posture by measuring what's called the angle of arrival, AOA, of radio signals. On the left, you can see a diagram of a transmitter sending out signals toward a person. The signals bounce back and are then received by an L-shaped antenna array. By placing multiple antenna elements in both the vertical, Z-axis, and horizontal, X-axis, directions, the system can measure slight differences in the time and phase of the received signals. These differences tell us two key angles: the azimuth, phi, which is like a horizontal compass direction, and the elevation, theta, which indicates height or vertical direction. Using these measurements, we can create a 2D heat map of where the signals are coming from, as shown in the plot on the right labeled Example of 2D AOA Estimation. Here, the bright spot in the heat map corresponds to the strongest signal reflection, typically the upper torso or head of the person. By analyzing how that reflection changes over time or across multiple frequencies, we can isolate different body parts, like the arms, legs, and even the feet. In the images below, we see real examples of this technique in action. Each pair shows a blurred-out photo of a person and a corresponding AOA heat map. Notice how each bright cluster in the heat map lines up with a different part of the body, sometimes the head, sometimes the arms, sometimes the torso. When a person stands with their arms raised or spread out, the system detects multiple distinct clusters at different angles, allowing it to map the person's pose. Where signals are captured at different time delays, or range bins. Each time delay, tau, corresponds to how long the signal took to bounce off a certain part of the person's body and return to the receiver. In the top row, the figure on the left, you see multiple heat maps labeled with different nanosecond, NS, values: 5.4 nanoseconds, 6 nanoseconds, 6.3 nanoseconds, and so on. Each heat map displays the signal intensity, in decibels, at that particular time slice. The red and yellow spots indicate stronger reflections, which usually come from body parts like the head, torso, or limbs. As we move through different time bins, we scan different depths of the body, gradually forming a silhouette. The bottom figure, or the second set of images, shows real subjects performing various poses, such as raising arms or crouching. Again, each image is a snapshot of Wi-Fi reflections at certain time delays. Over multiple snapshots, the system pieces together a complete shape or silhouette, which you can see in black and white on the far right. This time-of-flight method effectively ranges the human body. In this setup, we're using two main data sources to reconstruct human movement in 3D. First, we have a Vicon system, shown on the left. It's a professional motion capture setup, similar to what's used in movie or game production. The Vicon cameras track reflective markers on a person's body in real time, generating a highly accurate, ground truth, 3D skeleton, as you can see in the top middle box. Meanwhile, we also have standard Wi-Fi equipment, a transmitter and one or more receivers, that capture what's called channel state information, or CSI. Essentially, the Wi-Fi signal travels from the transmitter to the receivers and bounces off the person's body. The raw CSI data are then passed through several pre-processing steps: denoising, to reduce interference; segmentation, to isolate each movement interval; and transformation, so we can feed it into a neural network. The deep learning model, shown in the blue box on the right, is trained to map these CSI data to a 3D skeleton output. During training, the model is supervised by the Vicon ground truth, meaning it compares its predictions to the accurate skeleton from the Vicon cameras and adjusts its parameters to minimize error. Finally, once the model learns how to interpret the Wi-Fi signals, it can produce a 3D skeleton. See the constructed 3D skeleton on the top right, without relying on cameras at all. That means we can track someone's movements, even in darkness or behind certain obstacles, just by using regular Wi-Fi signals. In the bottom photo, you can see the actual lab setup, the Vicon cameras around the room, the Wi-Fi transmitter and receivers in the center, and a participant moving within the capture space. On the next slide, you'll see specific results comparing the ground truth skeleton from Vicon to the Wi-Fi based skeleton for different poses. This demonstrates how close the neural network can get to the real motion data, purely by analyzing wireless reflections. First, let's look at how Wi-Fi signals bounce around a typical room. In the diagram labeled A, you can see three signal paths: the direct line of sight, LOS, path between the transmitter and receiver, shown in blue, the reflection from static objects like furniture, also in blue, and the reflection from the person's body, shown in red, below that. In A2, we have a 2D AOA, angle of arrival, heat map. Each bright region corresponds to a strong reflection. One cluster might represent the low signal, while the larger clusters represent reflections from both the person, outlined in one shape, and the surrounding static objects, outlined in another. By separating out these clusters, we can see which reflections come from the human body and which come from furniture or walls. Next, in B and B2, we focus only on the static objects. Notice in the heat map that the human reflection is gone or negligible, leaving primarily the reflections from the couch or other furniture. Finally, C and C2 isolate the human body's reflection, which appears as a distinct bright region in the AOA image. Putting it all together, these diagrams show how we can filter out or identify different reflectors in a room. Essentially, the AOA technique maps where signals come from based on their incoming angles, allowing us to see what's static and what's moving, like a person. We take the AOA concept a step further by combining multiple frames over time or from different angles. Each frame captures a snapshot of the person's pose, highlighting where the signals reflect the most strongly. By stacking or merging these snapshots, we effectively build up a 3D or volumetric representation of the person inside a cube of AOA data. And the first few images at the bottom, labeled the first frame, the second frame, etc., you see separate 2D heat maps. When we add them all together, plus more frames in between, we get a combined 2D AOA image that reveals multiple body parts simultaneously, like arms, legs, and torso reflections. On the right, you see a 3D human figure inside a cube of these combined signals. Each yellow blob corresponds to a different part of the body, for example, arms at higher elevation angles, legs at lower angles. This approach doesn't rely on cameras or visible light, just wireless reflections. Finally, on the last row of images, you can see various poses: walking, arms raised, standing in a T shape, or crouching. Below each pose is the matching AOA heat map, showing exactly how the signals cluster around different limbs. The result is a rough but effective silhouette of the person's body in that pose, solely from the angles of signal reflection. Moving on to the diagnosis method slide, here, we see how computer vision techniques, such as mask RCNN or open pose, can be adapted to Wi-Fi data. In a typical camera-based approach, these algorithms detect silhouettes via mask RCNN, and then locate key body joints via open pose. For Wi-Fi signals, we often transform the raw channel state information, CSI, or angle of arrival, AOA, heat maps into a format that these neural networks can interpret. This might involve generating silhouette maps, SM, joint heat maps, JHMs, or part affinity fields, PAFs, just like we do with an RGB image, but instead we're using Wi-Fi reflections. By comparing these processed Wi-Fi images to ground truth labels, GT, the system learns to identify people and their poses, effectively diagnosing or classifying actions, whether someone is standing, walking, raising their arms, or even multiple people in a scene. The next set of images shows a person's limb movements as point clouds. Each colored point represents a reflection or data point corresponding to a limb position, like the wrist or elbow. The dashed lines indicate the trajectory over time, so if someone moves their arm in a large arc, you'll see a curved cloud of points. This is another form of diagnosis, where we're not just detecting that a person is there, but we're analyzing how each joint or limb moves in 3D space. That opens up possibilities for gesture recognition, physical therapy applications, or even sports performance analysis. Finally, we see a 3D skeleton progressing through different time steps, for example, lifting both arms from the start, arms down, to the middle, arms partly raised, to the end, arms fully overhead. Each of the blue dots marks a key joint, like the shoulders or elbows, and their positions in 3D coordinates, X, Y, Z. This sequence highlights how Wi-Fi can capture dynamic movements. From these data, one could diagnose someone's posture or motion, for instance, measuring how quickly they raise their arms, if they're symmetrical, or if they have any movement limitations. Looking at these two examples of Wi-Fi-based skeleton detection. The top image shows a 2D human skeleton reconstructed using 2.4 GHz Wi-Fi. You can see how the system draws lines connecting key joints like the head, shoulders, elbows, and knees in a single plane, like a stick figure in 2D. Below that, we have a 3D skeleton generated using 5 GHz Wi-Fi. Because higher frequencies offer potentially more bandwidth and resolution, the system can capture depth information more accurately. Now you see a full 3D model of the person's pose, complete with height and depth data. This progression from 2D to 3D demonstrates how researchers are improving Wi-Fi-based motion capture, making it more precise and informative. Wrap-up and future implications. In summary, these slides illustrate the growing capability of Wi-Fi signals to produce both 2D and 3D skeleton reconstructions using advanced machine learning and signal